start, and sorry for what's keeping you up Saturday. That's my last day in this visit. So I'll fly back to the Solomons to States, to New Mexico tomorrow. But for those of you who will be taking it for credits, and actually for those who want to continue in this format of projects, yeah, I'll tell you about that by the end of today, 2 lectures. So it would be great if as many of you will participate and not necessarily for grades. But I'll explain how we'll organize this later on. And as we move along, yeah, we are trying to be on time. And we must speak English.
No, that's to start on time in Russian means to start early.
Okay. So yeah, we have lectures in English, yeah?
Sure, yeah. Well, my understanding is that we have at least few books, maybe one. Never mind. So we speak English. Right. So what we managed to accomplish, so we got to that stage, and that's my plan for today. And then we have lecture 5 and lecture 6. But given that there are a few distinguished folks, it's any case custom. I already did it once, and that's what I plan to do. I briefly go through in this first 15 minutes, basically remind you what we've been doing, right? And then just to get you back to, because it's a lot of material rather than, so I'll spend 10-15 minutes reminding what we've been doing. So it's a story of graphical models, and it's actually a rather personal story for me. So therefore it's mini course based on more or less what I've been doing myself. So last time I was giving such course was already in 2011, and quite a lot of stuff happened. So actually the last 2 lectures will be focused mainly on what myself and others around been doing in the last 4 or 5 years. But in the course of those first 4 lectures we more or less reviewed how the story started. And not only for me, but in general, it's a rather new subject. So that was our basic model. And notation were changing, so we had not one graphical model, but number, and they're of course all related and can be restated, and there is a graph behind, and there are variables residing somewhere, either on vertices or on edges. In this particular case, for base model, it was variables were on edges, and variables maybe from some alphabet. Well, base example is binary alphabet, but it's not necessarily binary. It actually may be finite or may be continuous. So a number of stories, a number of discussions with continuous. So we have in this representation functions residing on vertices, variables on edges, and basic questions. A question of finding most likely configuration, or what physicists call ground state. There are many names in this business, depending. Well, there are many disciplines involved in so many names. So argmax, argument of max, so it's most probable configuration. So factors positive and some functions, so maybe constraints, or maybe really bringing some cost. And so you think in terms of probability, and you're finding most probable configuration, or you marginalize, and you ask a question like, what is the probability within this model of being at given edge, for example, that's where variables sit in this or that state, so plus or minus if you have binary alphabet. Partition function was most difficult object, and a lot of discussions were about partition function. Just normalization constant if you wish, but of course computing it, that is the key question, so how difficult it is. And we've been, that was early stages, so we discussed various applications, but yeah, so it was a story of complexity. So how complex algorithm for computing any of those three objects, maximum likelihood, marginal probability, partition function are. And I announced, well, few problems for which we have apparently easy computations. Easy means not linear. I'm sorry, not exponential. But in some cases even linear. And in fact, I'll be massaging this subject today more than before, so it will be specific problems. In particular, I'll start from planar Ising model story. In general, it's difficult, and right. So now, then it was this reformulation of the main problem of computing partition function in terms of as a variational problem. So you can state it as a comparison of measures. So you have this variational measure which we call belief. I mean, we use this word belief. Belief is a proxy for probability, and you optimize over this set of beliefs. So if your alphabet is finite, then it's finite set of functions which you optimize over under constraints, which is they should be probabilities positive and sum to 1. But if alphabet is continuous, that's of course well, infinite number of functions. So this Kubler-Klaber formulation, comparison of measures, allows you to compute formally, I mean, restate problem of counting as a variational problem, and that was key. Of course, it doesn't give you in a general case any gain in terms of computational complexity, but it's entry point for approximations. And mean field and belief propagation, that's what we discussed. Mean field is basically based on the idea of independence. So the second lecture was mainly about that. So we discussed mean field, we discussed belief propagation, but we didn't get to that through variational approach first. We first study this or analyze this tree story and dynamic programming, and then we discovered that well, dynamic programming allows, in the tree case, it can be restated as in terms of a set of equations, which we call belief propagation equations, and very early on in many disciplines, in physics, in information theory, people start thinking about applying those equations, even though they derive for trees, to loopy problems. And yeah, so it's and then we return back to this to this variational principle, which is exact variational principle, and we start discussing approximate variational principle. And mean field was the entry point, but then belief propagation, there were multiple ways of viewing belief propagation. Particularly, you may think as a correcting mean field. So that's correcting in the sense that mean field means independence. So variables are independent. So we joined your proxy probability distribution is decomposed in the product. Belief propagation, and we derive it for trees, but then we also gave a physical meaning to that. You basically have this correction for overcounting because variables were actually overlapping. If you assume that they're independent, it's missing a lot. And we've been basically deriving it, and that's following to what we call beta free energy approach with some references here and there to various people who derive it under different circumstances. We also spent some time discussing specifically not for partition function but for this maximum likelihood formulation. Most probable, what belief propagation gives as an approximation for maximum likelihood problem. And then we discovered that belief propagation is actually linear programming. I mean, that's what we call LPBP, linear programming belief propagation. It was actually, as with many subjects, I mean, many results in this field. I thought that it was first discovered by Feldman, Van Wright, and Carter in 2003, and that's what they call LP decoding. That certainly was exciting for me. But then apparently it's known from more or less 60s, well, not 60s, but 70s, in various disciplines. But in any case, so we have this discussion of LPBP, and LPBP actually, as opposed to beta free energy for partition function, is already gives some mathematical guarantees. It gives low bound for what we call energy. And yeah, so we started discussion of low bounds, and it was various yeah, so this, very briefly I was going through this story of polytope, what this linear programming is. It defined its linear function, and there is a polytope, this belief polytope, how you see that it's low bound. It's actually to start from big polytope and then do relaxations. That's how you figure out that it's low bound. Okay, so we went through that, and right, so then third and fourth lectures. So third lecture was focused on what is really key for kind of my personal contribution to this field. We've been discussing this gauge transformation. That's yet another way of looking at belief propagation, and you derive it not for trees, but as gauges, and you probably remember how I introduced those gauges, or reparameterizations. So it's transformations which keep partition function invariant. So there is this thinking, you keep graph constant, and you don't touch graph, but you start playing with those factor functions. And your rule of the game is that you want to keep partition function invariant. You don't want it to change. And so that's what we've been doing, and it was quite a lot of formulas as usual. We arrived at the same belief propagation equations in two different ways, and it was maybe, well, there are at least two ways. So one was this rule of coloring, and there was, so blue was colored, red was not colored, and well, we got this exact partition function was BP, and then the rest was a series, and the series is each term in the series is represented, it corresponds to a so-called generalized loop. We also had variational formulation coming from that, again, not linked to trees, and that's, well, we discovered that it's quite similar to this variational story which I was telling in a very empirical way first, the Freeman-White story. And this is this particular example, this loop series. So exact partition function is equal to Z naught is what belief propagation gives you. Yeah, and then the rest is a loop series. So I didn't emphasize at all algorithmic side here. So I was assuming that belief propagation, which is solution of equations, I can always find this solution. It's actually can be stated as optimization, which is not convex in general, and may have multiple solutions, at least one. We always have at least one, but how to find those solutions, well, especially absolute minima, or maybe local minima, I didn't discuss it. And there are a lot of discussions with that. I'll touch on this today, but that's kind of beyond what focus of this course is. It's a very important subject, and actually in projects, if somebody wants to jump on that, that's great. We will discuss it at length, and there are a lot to discuss here. But I kind of put it away. So it was mainly on the assumption that if there is this optimization, I can find the solution, and let's see what, because it's approximation from very beginning. I mean, belief propagation approximation. Yeah, so how to correct. So that was my focus. That's why I was calling it belief propagation NBO. Okay, so was yeah, so linked to this what is called reparameterizations, and right. So the last part, well, fourth lecture. I mean, last before what we'll get to today. I focused on a general methods which are alternative to this loop series, loop calculus. And there are a number of those, so we didn't discuss anything specific in the last lecture, specific in terms of particular graphical model. That's what I'll start to do today. In particular, it will be graphical model on a graph, which is planar graph. So that's what I'll start. But self-avoiding tree approach, cumulative expansion, generalized belief propagation, graph covers. So those are absolutely beautiful and what I see complementary approaches. So I'll not be using it today. So let me keep it unless will be some questions. Well, especially in this part of the lecture, I started to put, well, maybe I'll just show you things like that. This is a good subject for project, which is basically an invitation for you to pick it up as a project and then continue. And by the way, yeah, so updated, so that's the right website, so this courses. And it's well, all my courses are there, but there are not that many, so 4. So the one on the top is this. And this presentation is over there. There are also notes, which you are very welcome to read. And actually, like Oleg already started to do, there are a lot of misprints, I'm sure, in either of the two. I mean, those 2 files, please let me know if you'll find that. That would be great. But also look at this if you're interested in projects, because yeah, that's what there are a lot of opportunities for projects, a lot of open questions, and projects would be studying some particular paper. But then maybe if you'll be interested, we can talk about really research based on that, and a lot of opportunity for synergy between those different techniques or different ideas. So far, they kind of pop up in the last 10 years in various ways, maybe 15 years. There are a lot of open questions and a lot to understand. So this, computation tree. And by the way, I really appreciate you guys. I mean, asking questions and being a good audience. After previous lectures, I went back and I edited it, and I'm sure I'll do it again. So in particular, I realized that last time, for example, I didn't discuss computational tree. I mentioned it, but didn't discuss some new slide. But please read it. So it was this covalent expansion story. Yeah. So basically, a number of those rather technical but interesting junction tree, graph covers.
What about graph covers?
Grisha, you miss it. Well, you heard it. It's Pascal-Ventaber story. Probably it's Ralph Cotter originally. Yes. Ralph Cotter and Pascal, and it came from information theory, but it's actually quite general, and there are cool results. In particular, relation between belief propagation and exact in a very unusual way. So if you have graph covers of high enough, you need to send it to infinity, high enough order. And then you consider all possible covers. For each of them, you compute exact partition function, and then average over them equal weight. Take the square root of order m. Take limit, you get belief propagation. So it's a very. And I mentioned that I actually didn't go through. I would love to understand in details how they did it. I didn't go through that yet. Okay, complementarity, so that's I mentioned. And okay, so that's briefly what we've been doing so far. And now, specialized graphical model. That's the subject for today. Of course, I don't pretend that I'll cover all possible graphical models. There are a lot, and there are a lot of special things, but it's rather personal story, well, because on one hand, it's easy for me to say it this way, but there is also I mean, not a lot of stuff. Well, I'm mentioning also bulk of others, but well, it's just easy for me to do it based on what I was doing. Right. So it's actually a list of things which I was doing from 2000 to 2011. And why 2011? That's when I was giving at Yandex and Fister, well, similar lectures, but actually it was much less focused on pedagogy on students, but also rather on researchers already kind of more mature. But in any case, well, we had generalization of this loop calculus for high alphabet. That's what we call this Volodya-Cherniak loop tower. And then we discovered actually that there are many ways of doing it. So it was one rather early thing. That's how I got to know David Gamarnik, and we collaborated on applying this technique to counting independent sets. Maybe here important emphasis is that belief propagation normally is believed to be very accurate, and but for particular graph is not exact. And there are a lot of stories which basically would be focusing on figuring out why, in some average sense, belief propagation performs well, not for one particular model, but for ensemble of models. It's more like information theoretic type of approach. You can see the many models. You even take this what we call thermodynamic limit of infinite graph, and make some statements. And in particular information theory, there are a lot of very beautiful results. I'm not touching on that. I'm more focused on algorithmic aspects for particular graph, finite graph, etc. But in this particular paper, we actually mixed. So it was particular graph, but then we tried to make some statements using loop series and basically showing that in some average sense, those corrections are small. So there are basically for me two kind of directions. One case uses loop series to show that those corrections are really somehow insignificant, but more interestingly is to overcome, well, basically when corrections are cannot be ignored, try to sum them up and try to come up with improvement of belief propagation, which is still tractable. And that's what I'll be mainly focusing, and that's what some of those stories. So I'll start from planner. So what does Mark has read? What I plan to cover? Well, I also Mark read things like basically again emphasis on incompleteness. So there are open questions which I very much would appreciate if some of you would pick up as a subject for project or research. I'll tell some story about permanent, and yeah. So I'll tell you about some matching problem, well, which is of course related to permanent, but a little bit, well, it actually will be what we call BP blossom. In the last lecture, well, we will make a break after an hour. It will be first attempt to mix Markov chain Monte Carlo with belief propagation. And I didn't mention anything about Markov chain. Markov chain is, of course, also a very legitimate way for asymptotically exact, but in practice approximate way of answering, well, all those questions I mentioned, but specifically partition functions. So it will be a mixed story, which is very recent. And here, well, actually those two stories are really, well, three stories. I go more or less from this year. This is more like applications and application energy systems. That's my main application domain for me to focus on. And well, I'm very glad that there is kind of convergence of my application side and this theoretical side, graphical models. Well, this is machine learning. And maybe some of you already heard, I gave a talk on that, it's called TEC in the spring, but probably not. Maybe it will be one or two. So that's a plan for today, models. And, all right. Okay, so now, right. So now, when I say specific graphical model, concrete graphical model, it's special and concrete either because graph structure is special or factor functions are special. Okay, so what I've been talking so far was mainly generic. So being very pretentious and doing all these transformations, but not limiting ourselves practically to any specifying assumption. Now I want to focus on specific graphs, specific factors, and we'll see that this will allow us to discover some situations where computations are easy. And most famous story, which I'll start, is actually, most famous, probably most famous story showing overlap of theoretical physics and computer science is the story of, well, Blasey Ising or Dimer models on a planar graph. So this Ising model I already introduced. In one particular graphical model, well, in this case, in Ising model, we put variables on vertices and functions or interactions are on edges, and they have this exponential form. And of course, that's a model which is extremely popular in machine learning, in computer vision, and many applications too. It basically model is general purpose, practically general, almost general purpose model for what we call pairwise binary variables, for binary type variables interactions. And now imagine that we have planar graph. What planarity means? Well, this is planar, so when I put it on a plane, I don't have edges crossing, right? So there are no overhangs. Otherwise, there are no restrictions. So it doesn't need to be lattice. Physicists always thought mainly about lattices, but it doesn't need to be lattice. And well, another class of problems for which it applies, and it will also be planar. So I want it to be planar. It's what physicists call dimer model, but it's a perfect matching problem. So basically, perfect matching. Well, actually, this funny graph I draw it because those two models are in fact equivalent. I didn't want to play on that, emphasize it, but you can get from this model to that model through some transformations, and actually graph transformation, but which will keep planarity. So basically, what perfect matching means, it means that your variables now are on edges, and you have a constraint that variables which sits on edges which are neighboring, which are edges emanating from a vertex, only one of them is colored, or only one of them have a state 1. All others are 0. Okay? So matching, but also perfect matching. Perfect means that it's exactly 1. Matching usually means that it's either 0 or 1. Neither of them are colored or 1, not more than that. Well, and you also have weights associated with edges. So that's how formally partition function is defined in this case. And again, if it is planar, you would normally say that, well, it's a difficult problem, but it's not. And it's not difficult, and it's a really long story. It's probably the most important story in theoretical physics of last century. It's related to these phase transitions, and actually there are a lot of stories in theoretical physics behind that. But remarkably, there are consequences, computational consequences, which people kind of overlooked. So it was, well, more or less, if Anzager or Katz, famous mathematician who worked on this problem, if they would really ask the right questions, they probably would answer it in 40s and 50s, but it took some years. And actually, Castellian and Fisher, they are physicists, but Castellian kind of started to put it in a more or less computational format, and Francis Barahona in 82, well, 40 years later, more or less pinpointed and formulated as a computational complexity problem. And by the way, he is at IBM Watson, well, active researcher over there. He is originally from Chile, I think. And the story is, I'll state it for matching, for perfect matching, and let's take this simple graph. And in this case, well, again, matching, perfect matching is I need to color edges, and my legitimate coloring, so legitimate perfect matchings are basically 2 in this case. So if I color 1, 2, then I also need to color 3, 4. And constraint once again, each vertex should have only one edge next to this vertex which is colored. So if I color 1, 2, and 3, 4, that's actually shown here. That's one configuration. That's another configuration. That's it. So nothing else is allowed. There are only 2 configurations. Okay? Remarkable statement is that this can also be understood as a square root of determinant of a matrix which are constructed from those weights which are associated with weights of edges, but with kind of funny plus and minuses put in there. And this funny plus and minuses, the so-called odd phase Castellian rule. So this Castellian who actually physicists turn into computer scientists. Yeah, so this is a formal description of this Castellian rule. Direct edges of the graph such that for every internal phase, the number of edges related clockwise is odd. So it's kind of, well, and to explain why it is so, I'll need a separate time. It doesn't. I mean, I didn't plan to do it, but in fact, it's really good if somebody will pick it up a project. It's can be understood in various ways, and by the way, there is very fancy way and actually very nice way to understand it through so-called fermions, that's term from physics, or Grassmann variables, as more mathematical terms. But that's probably most remarkable example. Example of what? Again, of course I give you example only for a very small graph, but it's generalizable for any planar graph. In a planar graph, you can always introduce this odd phase Castellan orientation, and then partition function, which generally, remember, right, so there are exponentially many terms, is reduced to square root of determinant, or what is called Pfaffian. Determinant, as we know, right, so we can do this decomposition, right, so it's n cubed, actually in the worst case. So in the planar, it's reduced to n and 3 over 2, I believe. So there are these fancy ways of diagonalizing matrix. So it's basically a tremendous and very serious reduction of complexity. Okay, so that's useful to know and can be understood, and that's Francis Barafone work. But what Francis did also, he focused on not only on dimer, but on extensions of this dimer model. Dimer is again the perfect matching. And there is so-called extension dimer monomer, or in the world of computer science, it's usually called just matching, not perfect matching. And difference, again, I already told you, difference is that you now allow some vertices to be absolutely not colored. So it if one edge colored, only two are not allowed still, but it may also be that no vertices are allowed. This minor modification, just 1 second, I'll finish. This minor modification, this extension from perfect matching to matching, kill this solvability. So immediately it will be exponential complexity. And respective story is that in the Ising model, so if I'll get back to Ising model, if I add the linear increment here, I'm bad. I cannot. Well, it's not reduced to Pfaffian determinants. Yes, Robert.
Can you give some example of this perfect matching problem, which is described by this Pfaffian?
We'll actually get. Oh, you mean practical problem?
Yeah. Like
so applications.
What is like?
Can you
describe this way?
Can you hold it, because it will be some story. I didn't plan to dive into application, but I'll be discussing computation of permanent and right. I'll answer your question a little bit later. So there are examples from fluid mechanics. Well, matching in general, you know a lot of matching problems. Let's say you have two consecutive snapshots. Let me give it now. So you have camera and you have physical experiment, for example, and there are particles which you follow. And you assume that no particles are lost, right? But they kind of move around. You take one picture, you take another picture. And particles are identical. You want to figure out which particle went where. So that's an example of perfect matching problem. Well, it becomes matching if some particles are not matched, if there are more particles or less particles. But in this case, it's also bipartite. Well, there are all these problems like matching couples, right? So there are, I don't know, 10 women, 10 men. How to match them based on their, well, you introduce some features, right? So maybe there are constraints. She or he prefer blonde, or, you know, there are plenty of matching problems if you want. So now, planar matching problem, that's where geographical proximity is usually important. So basically, when you observe from satellite and you want to introduce, well, you know that there are some geographical relations, and that's when planar matching problem would appear. Well, but there are plenty. Okay. Right. So now it's of course famous. I mean, In fact, not super well-known story. I wish it would be in the textbooks, both on the physics and the computer science side, but it's not. Another rather famous story, but famous recently, is by Valland, who is at Harvard, and he is rather famous for. Actually, he's the person who introduced this class of complexity class Sharp-P, which is exactly for partition function. It's counting and characterization. I mean, Sharp-P problem is more or less problem of computing partition function, and so it's well, originally it was for just counting and partition functions weighted counting. It's a little extension. So and Valland, I didn't know it when we've been doing this story of loop calculus, but actually David Gamarnik attracted my attention to this very nice set of work, and Valland was actually doing the following. He knew about this Barahona story about planar models which are easy, and before Valland it was relatively, well, basically those two, dimer or perfect matching problem on planar graph and Ising model without magnetic field, known to be solvable through this determinant solvable, so not complex. And what he asked himself, he asked, if there are other problems like that, which are in the planar world, which are easy, in the same way easy. And he introduced what he called holographic transformation. And the reason David attracted my attention to that is because for him, for David Gamarnik, they look like very much like our gauge transformation. Indeed, they're very much related. So basically, Valland, he was more like, it's a very funny paper to read. It's actually also maybe a very good project for some of you. He didn't start, I mean, from this logic that I have this easy model, which is, let's say, planar Ising without magnetic field. I start doing these transformations, keeping partition function invariant, and I discover a new problem, which is, well, through this transformation equivalent, and therefore easy to do. He did it completely in reverse. So it was like, I don't know, a focus type of thing. So he started producing one by one. I mean, it was in this paper like 10 different models which stated and look very difficult. And then he said, no, they are not difficult. In particular, there is this ice model. There are many, as I said, on a scale of 10. But my understanding is that what he did, he first did it, I mean, he started from this dimer model or Ising model and applies this, he called it holographic transformation. I actually still don't understand why he called it this way. But, so he discovered new easy models, and so when we learned about that, we more or less started to play with that too, and that's the first little story. And one thing which so we focus on a planar case, and we restricted ourselves to planar graph where all nodes are of degree not more than 3. Well, it should be at least 3, otherwise it's not interesting. You'll get a bunch of trees not connected, and trees belief propagation is exact. And what we figure out that there is as you remember, we have this generalized loops, right? So we have belief propagation, which is obviously approximation, and then we have this finite series, and series is over all loops. And of course, generalized loops, the number of those generalized loops is exponential. In general, it's bad. So you cannot claim these computations, exact computations, easy. But then we discovered that a subclass of those generalized loops, some resummation of some of those terms, can actually be performed in an easy way, and in fact, on a planar graph, that's done through mapping of this whole subclass to this perfect matching problem. So I'm not giving you all details, and again, it's another possible project for one of you, possibly, but it is stated in here. So summing is what we call two regular, well, you can also call it closed curve partition, is easy. So what are two regular? Two regular is basically when you have contributions like that. So you have each vertex within this colored structure having only two edges colored. So you remember that, well, over here, there are in particular this type of contribution. We ignore it, but we account for this type of contribution. Or for that matter, this contribution individually, maybe that contribution, or this contribution. Also, this one. So if you limit yourself only to those contributions, then you can, so basically you completely ignore everything else. Then you can show that this series itself, you can think of it as also graphical model by itself after you apply this belief propagation. Then you can sum it up and you can map this series to this perfect matching problem on a planar graph, and you basically compute this sum as a determinant. So that was our first statement, and then actually in this paper with Kapin and Gomez, we more or less went beyond that and we explored it as an approximation empirically, and we wanted to ask ourselves how good is approximation, and well, from what we saw, it was reasonably good, but we were not able to make any mathematical statements like that this estimation is estimation from below or estimation from above. In general, those other corrections, they were sign, not alternating sign. So actually, this still remains kind of from what I see, kind of open problem.
This approximation of what? For matching?
No, it's approximation for partition function. So it's a weighted counting. In original problem you have is arbitrary problem on a planar graph. Arbitrary graphical model on planar graph. And basically what I'm saying you first compute belief propagation. And then you're getting this what we call loop series, which is by itself can be understood as a new graphical model. And in this new graphical model there are many contributions, and I down select still exponentially many terms, but not all of them. I'm saying that if I down select terms, which are what I call two regular closed curve terms, which what I illustrated over there, and doesn't matter how big is the graph, then I can sum them up with efforts which are polynomial, actually n cube in the size. So that's what I'm saying. I cannot provide guarantees for this approximation, and that's, I would say, kind of open problem. If for some subclass of this problem, planar problem of general position, we can do. But then we also ask ourselves a question: fine, in general it's still difficult. Can we classify problems which are easy? And it's more or less along the lines of this Valent approach. Valent certainly provided a number of planar graphical models which are easy, but it was clear that it's not, complete description of all possible easy planar problems. And we also not claiming that we describe in this way all possible easy problems. So it's more like only one way. So we can describe quite a lot of those problems, and we do it more or less through loop series. And what do we do? So again, we apply this belief propagation. We are getting loop series, and then, as you remember, all terms in this loop series, well, each associated with generalized loop, can be computed based on these beliefs which we found solving belief propagation equations. And each term consists of a product of terms there is a concrete formula to compute this. In particular, there are contributions from nodes of different degree. And if nodes are of degree 2, based on what I just told you and showed in the previous slide, we can sum all those contributions. And then we ask therefore the following question. How about classifying all problems for which these colorings, which are 3 colorings, and that's why we restrict ourselves to degree 3, they're 0. And if they're 0, then more or less the summation which I mentioned in the previous slide, we can do explicitly, it reduced the determinant. And yeah, so that was our way of classifying those problems. So basically, by forcing the 3 coloring to be 0. And we also realized that we can do it in reverse. So we can start from a graphical model, but basically from graphical model where this degree 3 factors are 0, degree 1 are absent, and then we can apply any gauge transformation which keep, well, important thing in this approach is applying this gauge transformation but keep all terms positive to have it interpreted as a probabilities. So if those conditions are met, therefore we can do it in reverse, and we can classify all problems, well, not all problems, but rather large set of problems which are easy. Right. So that was this story. Well, I more or less said it in words already, and right. So now. Step which I'm not discussing today, in part because it's even more involved mathematically. Well, this mathematics is very simple. It's more or less straightforward algebra. Well, the one which I'm mentioning, which we needed to generalize the statement for degree more than 3, requires something else. It's actually also generalizable to not only for planar graph, but for surfaces. Surfaces of finite genus, for example, it's torus. Is genus 2. Well, it kind of requires a little bit of topology, and I really didn't feel that I have enough time to cover it. But that's another very good and very difficult project because it requires mathematics and thinking which is beyond what I was explaining. But if one of you want to pick it, that's great. So we have some paper with Chimniak on that, and actually there are a lot of open questions. There are also very beautiful mathematics coming from Rishitichin, who is at Berkeley, which is very much related to that. It's also, there are some relations to quantum computations in this story, actually significant relations, which I'm not claiming I understand, but would love to understand. Okay, so yeah, so it's kind of marathon thing, right? let me go to the next subject, which is, well, to a degree related. So now it will be story of permanence. So what is relation? Relation will be through this perfect matching, but now I'm changing settings, so it's not planar graph any longer. And what is permanent? You have graphical model, which is bipartite. So you have vertices which I mentioned, which are colored red, and vertices which are colored green, and they're only connected to each other and not within themselves. So reds have no connections between them. And connection in our graphical model world means there are no variables. Variables will be sitting on edges, and so there are no variables which will be residing only within this red. And
multiple edges going from.
Right. So, well, in particular, this is example which I gave you, these 2 snapshots, right?
No,
so you have.
So if 2 edges are possible going from.
Oh no, it's not. So you have, again. Let me restate this application. So you have camera, and you're taking pictures, and you see bright spots, and you do it, let's say, minute aside, right? And those bright spots are moving. They're live particles, so maybe fluid mechanics behind which you don't see. Maybe you visualize this fluid mechanics with those.
No, but in that case, if some of bright parts went to like other points, it candidate went to another.
Okay, so you have one perfect matching, which is physical, which actually happened, but you don't know which, and therefore you consider all possible options. Okay, and well, there is some machine learning problem which actually will involve computing partition function in this case. So you, well, finding one configuration may be maximum likelihood configuration, but if you don't know interactions, you may want to introduce this partition function. Partition function means that all those perfect matching. So perfect means that this particle is linked to that particle, and well, there is basically pairing of particles, and all number of particles here and number of particles here is the same. So there is a perfect pairing, but there are n factorial of them, and you sum all of them, and each contribution comes with a weight, and well, let's say you have a weight, and weight resides basically weights associated with each edge, and some particles may be closer to each other, and therefore you encourage them. That's just an example. So this is a formal definition, and you can also understand it as what we call permanent of a matrix. So a matrix, so what I just explained, this relation between particles, you have n particles here and particles there, so it's a square matrix, and you put weights, basically, so there is, let's say, particle number 1, particle number 2, so it will be element 1, 2, and 2, 1. So now what is different between permanent and determinant? Right? Well, there is a matrix, natural thing is to compute determinant. If you compute determinant just, term by term, remember, right? There are plus, minuses, plus, minuses. Permanent is kind of looks simpler brother or sister of determinant. Everything is plus. It's really partition function, so you sum over configurations. And remarkably, it's immediately difficult. So determinant, to compute determinant, we can diagonalize, and it's n-cube complexity. To compute permanent is, well, in general, n factorial possible terms, and it's a difficult problem in general. So now, what do we do about it? Yeah, so that's the next story, and well, you can apply belief propagation. Never mind that the graph is dense, so there are, certainly not 3. We remember that belief propagation is exact on 3. That's what people started to discuss, and well, in this case, belief propagation is rather straightforward, and in this case, you can, well, you actually can, in belief propagation, as you remember, the way I was presenting, I was introducing beliefs associated both with vertices and with edges. And my variables reside, original variables reside on edges, so that's naturally what I can do. But for this specific problem, remarkably, I can completely express beliefs associated with vertices, which are more complicated objects, through beliefs associated with edges. So these betas which you see in here, well, you remember probably my notation. So I was introducing belief associated with edge AB, and the sigma AB is 0, 1. So if edge is present, it is 1. Sigma AB 1 means that edge is on, and sigma AB 0 means that there is, well, there is color, it's colored, and this is not colored. So now, what I introduced beta is here, beta AB, is actually BAB 0, I'm sorry, 1. So it's a probability that H is colored. All other beliefs, in particular this BA sigma A, can be expressed for this model in terms of just this beta. So it's just one scalar variable, which is of course in between 0 and 1, between because we expect it to be probability. We have as many of those as number of edges, but we can reduce our beta free energy description to that. It's only for permanent. And that's how permanent, beta free energy, or F for permanent, look like. So mu's are weights this multiplicative weights which you had for each edge. So it's this nice, well, what I was calling self-energy term, and those are more or less standard entropic terms. Look, yeah, so right, entropic terms. So b log beta log beta, and well. Okay, so sorry, this is still exact free energy, so it's not beta free energy, it's exact free energy. Okay. And I also have set of constraints, and this set of constraints is this polytope in this space. And so now I'm getting to this beta free energy. Yeah, so right. I'm getting to beta free energy, and so in this case, sorry, I misspoke. So reduction, which I started to discuss, reduction is for beta free energy, for approximation. So here, in exact formulation, yes, I do have this beta AB, which I was already explaining, but I also have this entropy in entropy term, an exact entropy term. All possible betas, and it's much more complicated expression. But in the case of beta free energy, I'm reducing only to betas associated with edges, and now for a logarithmic part, you see that there are two contributions, right? There are two types of contributions. There are, as usual in the beta free energy case, positive and negative, and that's what breaks convexity. So this type of expression was derived by Pascal van Tadel, and so there is this polytope over which you want to minimize this beta free energy. And in general, beta free energy in this type of formulation, well, because of those negative terms, is not convex. But here, Pascal managed to show that it's completely convex, and it's actually not trivially convex. So you need to account for constraints, well, for the structure of polytope. And that was already surprising, because normally for generic graphical model we didn't have this convexity for beta free energy, which is general approximation. So he didn't discuss going beyond approximation, but approximation itself, having it stated this way, convexity was kind of useful. And well, convexity then, well, useful property in particular for solving belief propagation equations, because you can claim that there is one solution, and in this particular case, equation seriously simplified. And then even more interesting story started. Well, that's how we enter this field. So we started to play with our loop series in this particular case, and we discovered that, well, very much like I was telling you about the planar case, so there is some resummation which was useful, but in the planar case we were not able to resum all terms in the general planar case. Here we still cannot really resum, I mean fully, but there is a very significant and serious factorization. So what is written in here is, so this exact permanent, this is what is efficient and easy to compute, and well, it's a convex optimization problem which is behind, so complexity of approximating it is very easy, I mean very low. But this is a generic expression for permanent for perfect matching of loop series. So each term in loop series will expressed in a concrete way. But then there was expression through some mixed derivative of function, functional which is very nice and compact. But then, and when I we got it first time, I thought that we more or less solve a difficult problem, but of course computing mixed derivative of nth order is difficult problem by itself, even if your function is have a explicit expression, so it's exponential in complexity too. And this is expression which is probably most useful for further discussion. This is expression well, we call it a term, BT term, in the following sense. So we started from permanent, and we have this BP expression, which is that. And then what is left appears to be also permanent, but permanent of another matrix. You remember, right? So I started from, well, it's my graphical model for perfect matching, but I can interpret it as a computing this permanent of a matrix, n by n. And I'm saying that the whole loop series, corrections to BT, what I'm interested to estimate, is another permanent. This is not a useful statement in terms of complexity, or at least not for now, but it's an interesting relation, which is in general do not hold. So I start from, basically it's a similar type of expression which I'm getting. I started from permanent and I got, if I want to go beyond belief propagation, permanent. And, but then it also had an interesting overlap with some really non-trivial, well, there are basically two directions. So maybe I'll skip this one in the interest of time and go to maybe a little bit more mathematical statement. So here, just very briefly, with Adam Edidia, who was, by the way, well, you probably remember this name already mentioned, but same family name. So Jonathan Edidia is the senior researcher who introduced belief propagation as a beta free energy. So Adam is his son, and he was working with me as an intern, and it was second year undergraduate student, and he did really extraordinary job. So he spent 2 summers at Los Alamos. So what we've been doing, we played with the generalization of BP, and generalization uses gamma. So normally in belief propagation, this gamma is -1. But we thought to play well with the gamma, and we discovered that we actually can generalize this what I showed you on the previous slide, this perm BP term for for any gamma. And then we also discovered that when we go from -1 at -1, empirically we saw that we are getting low bound for partition function, and somewhere higher gamma, at higher gamma we actually cross actual value. And we've been able to show, even mathematically I would say, well, mathematical physically. So we didn't put it as a proof, but I believe there is a proof behind, that there exists gamma in between -1 and 1 for which this generalized BP is exact. We cannot find it, but we know that there exists one. So it was more like empirical study, but mixed with some analysis. And then, I ran into Leonid Gurvits. And Leonid Gurvits, I don't know, Grisha, if you know Leonid Gurvits. Well, he is rather famous for a number of papers about permanence. Well, by that time, he also started to be interested in graphical model, and he comes from he's very mathematician. And he makes this, well, in a very algebraic way, and nothing to do with what I will discuss here. He made this statement that in my language, I can reinterpret in the language which we use with Adam, that if I pick for this gamma -1, which corresponds to belief propagation, then it gives a low bound for permanent. And it was a rather trivial statement. Okay, and then, but this statement was based on Schreiber, another very famous computer scientist and mathematician, algebraic statement, which is, I really cannot understand this paper. It's very dense and very difficult, but result can be stated in a very simple way. And remarkably, well, you see probably that the structure which, well, okay, let me state it. So you have a matrix which is doubly stochastic, which is a matrix of betas. Doubly stochastic means that if you take any row of the matrix, first of all, each element is in between 0 and 1. And you take any row or any column, that's why it's doubly stochastic, and you sum up all elements, either along row or along column, you're getting 1. So basically it's a probability matrix, right? And so if you take, if you have Is probability matrix, double stochastic matrix, and you construct this matrix which we put in here, which is like that. You pick, so this is product element by element. I use just, I guess, MATLAB notations. So you pick one element, you have another element which is 1 minus beta, and you just multiply them element by element, and you form a new matrix. You compute permanent of it, and it's bounded by this value. It's very non-trivial. But now, a remarkable statement which we, so this object is exactly this object if you look at, well, yeah, I produce it here. I put it for any gamma, but this object is more or less correction to our belief propagation. And well, for gamma minus 1, it's exactly that. And more or less, this rather non-trivial statement of Hurwitz follows from this Schrier and this our formula of term between term. So that's what we found. So there is probably a lot of other interesting stories behind. Actually, Hurwitz conjectured that well, remember I was mentioning that this crossing. So at gamma equal to -1, we have low bound for partition function given by belief propagation. Hurwitz conjectures that, in our language, he did it in some other language, that at gamma equal to -1/2 will give upper bound. Nobody, well, he didn't prove it, we also were not able to prove it. Empirically, with Adam we check, and that seems to hold. So that's actually a very interesting open mathematical question if somebody will be able to prove it. It actually have multiple consequences in this mathematics of permanent, and there's a beautiful mathematics behind, and I'm not claiming I understand it, but there is really interesting and unusual connections. Okay, so right, so there are now. I wanted to get to actually last subject of this lecture, and that's probably okay. Well, okay, we have two options. Either we call a break now, or we'll extend it probably for another 10 minutes, and we'll be break in 10-15 minutes. So what do you prefer? Okay, let me maybe continue, and I'll try to more or less finish this lecture, and then we'll go into break. So it's another story, and now story, it's actually very much linked, so there is this relation between stories which I pack in this lecture. So I first was talking about planar problems, but one particular planar problems of interest was this planar perfect matching. And I was computing partition functions. Then I moved to permanent, and permanent is a perfect matching, but now for bipartite graph. And here I'll be discussing not partition function, but maximum likelihood problem. So optimization problem, combinatorial optimization, which is perfect matching, well, what's called minimum weight perfect matching. And actually this problem is known to be easy. Easy in the sense it's not exponential. And it's probably one of the first very non-trivial easy problems which was discovered. And it's a famous work of Edmonds from '65. And Edmonds called it Blossom. Because of specifics of construction of how he solves this problem. And his algorithm is rather involved. And I actually will not be discussing in details his algorithm. But in this story here, what we discovered in that work with Jinwoo, a number of authors I'll actually put, but Jinwoo Shin and his students are main contributors. Jinwoo was actually a student with me. He was Deorat Shah. Deorat Shah is professor at MIT. Jinwoo was student of Deorat, and he spent 2 summers at Los Alamos as an intern with me, and now he's professor at KAIST, and there is already next generation of students from Jinwoo, coming to Los Alamos to work with us. Okay, so this is a story of the following type. If we put this problem on a bipartite graph, which is what I was discussing before, but not partition function computation, maximum likelihood. Then we discovered that what I was calling LPBP is gapless. And this is by itself very interesting and non-trivial result, but it only holds if your graph is bipartite. If your graph is not bipartite, so you are looking for minimum weight perfect matching, LPBP will not be exact. And therefore, when we started to think about it, on one hand, we know that there is some algorithm which is polynomial. On the other hand, we know that BP is not exact. And we thought it's a perfect example for us to figure out how to close this gap, because most probable, we were not sure, but we thought that we will be able to close this gap. And that's indeed what happened. And we close this gap well, there is this characterization of our algorithm. The termination is guaranteed is n squared n is the size of LPBP running time, because at every time, every step will be running some kind of LPBP. And another interesting thing about this algorithm, this approach, is that we'll be using some gauge transformations, but we'll also be changing graph, and we'll be changing it in steps. And that's, as you may remember, there was something which I really wanted to combine. I mean, this gauge transformations, factor transformation, and graph transformations. Yeah, and in terms of Edmonds algorithm, so it was evolution of this Edmonds algorithm. So original Blossom 1 was introduced by Edmonds himself. Most recent is Blossom 5. There is actually a C code which is available online. And this is Vladimir Kolmogorov, who probably is known to some of you. He is at Vienna, and he actually, so he is also of this Blossom 5. So that's benchmark for us. So we wanted to compare, and I'll be claiming that what we produced, what we have, we call it Blossom BP, which is based on belief propagation, which is exact algorithm, and it's actually performs, at least in theory, better than Blossom 5. In terms of implementation comparison, we are still, I mean, it's a recent story, so we are still, we need some time to really compete with Kolmogorov on that, but we are pretty sure that we'll probably beat it. Okay, so why you should be surprised about, I mean, what I just told you before, well, just now. So BP in general is good for trees, but now I'm saying that it's good on graph with loops, and actually a lot of loops, many loops. And also because it's a non-trivial construction. It's not like I'm closing gap in one step, so it's a number of steps. Well, I think I already answered this question, why we picked this model. Well, in part because we've been playing with these perfect matching models. But motivation was that, well, we already knew a lot about these models, but also we knew that problem which we are trying to solve is polynomial, so it's not exponential, and it's non-trivially polynomial. So we wanted to figure out how to beat it, if we can do it with belief propagation, and apparently we can. And what I'll give you here is a schematic, of course, in 10 minutes, schematic view on how we proceed. And well, another important thing about matchings is that, well, there is this LPBP, and LPBP was part of my studies, right? So that's for maximum likelihood formulation. So it's linear programming, but a very special type, and it's motivated by data. For perfect matching, actually on any graph, this LPB perfect matching, actually stated in here, it's a integer programming, right? Because that's perfect matching stated in original variables. So you have this x, which is 0, 1, and this curly brackets mean it's 0, 1, so it's integer programming, and there are weights, right? And there is this perfect matching constraint which I put in here. Belief propagation introduce the LPDP, introduce some linear programming, right? And linear programming, which in a case of bipartite graph, is actually gapless. That's what I told you before. In general, not, and that's important. But LP, which another LP, and not just relaxation of original integer program. What would be relaxation? Relaxation is actually written with that. You replace the 0, 1 by any value from interval, right? So your variables are any value from it. But the special thing about those relaxation is that standard relaxation of this problem and LPBP, they're actually equivalent for this class of problems. In general, they are not, and they're very different, because this LPBP, I can get it even if I start from integer nonlinear programming. But in this case, I start from integer programming, and I got the same. That's a special feature of these perfect matching problems, and which is quite unusual. So now, a remarkable thing which, well, you see it marked by green, and that's actually from Edmonds, and that was prerequisite for his algorithm. Edmonds discovered that if you do relaxation, you have a gap. He understood that. But then, if you add a set of nonlinear, linear equalities, which stated in terms of odd sets of vertices. So basically, you should have number of vertices which equal. Then S is a cardinality of a particular vertex. If you add those constraints, which are actually satisfied for 0, 1 variables, but you add them to this linear programming, then you completely close the gap. Problem is, so that was the first observation of Edmonds which led to his remarkable blossom algorithm. But unfortunately, a number of those constraints which you need to put is exponentially large. But the key thing for Edmonds' algorithm was he figured out how to, not going through linear programming, but going in these very strange graphical transformations that you can kind of reinforce and using those additional constraints as a guidance, basically to find a solution in polynomial time. By the time Edmonds was solving this problem, nobody was able to provide a sequence of linear programmings which are in a polynomial number of steps solve the problem. Well, it took whatever number of years. In 2012, those authors suggested a way of doing it. And more or less, it's more or less standard cutting plane technique in optimization. So your key thing is that not to use all of those constraints, but pick the right one and do it iteratively. So basically, if you ignore this constraint and you solve this problem, you're getting non-integer solution, which is clearly not optimal. It's not a solution of integer problem. And you want to, but you're of course getting low bound. You want to add constraints one by one, and you want to select them in a smart way, and hopefully not exponentially, not do it exponentially long. And that's what those authors suggested. But their way of doing it was very complicated, and actually, but that was another motivation for us to go into that. Okay, so maybe I'll just kind of put things on the rack, and will not go into all those details.
It's your American English. Put things on the rack. I'm not sure that everybody understands.
Well, you just put a rack and you hide what is very precious, but you don't want to discuss on the rack. Yeah, so that's what most probably I'll do. Let me, just in the interest of time, because I really want to save energy for this last lecture. So there is basically a very concrete algorithm which is based on a maybe one thing. I'll not tell you algorithm itself, but I'll tell you what is a basic formula which kind of theoretical part which helps us to develop this algorithm. And it's actually was rather long distance from this formula to algorithm, but still I believe it's probably the most important thing. You remember my term well, what is called term equal to dt times term, right? That was for partition function. I was saying that partition function for permanent was my computation within dt, but what was left is a permanent thing. So this is maximum likelihood version of that. So I start from integer programming. I'm getting naive relaxation, which is equivalent to LPBP. So it is equivalent to solving this belief propagation equation. And what is left is a new integer programming. And this new integer programming on the same graph, but ways which are changed. Okay? So that was a key thing. What we needed to add, and that's why we call it bootstrap. And first it was heuristics, but then we managed to prove things and basically turn it into exact algorithm. We managed to contract graph. So basically the logic of this algorithm, well, which is schematically I put it in here. Maybe I'll just show you. No, I'll not show you. Well, there is somewhere a link to illustration of how this algorithm works. But more or less, what we are doing is the following. We start from original graph with original weight. We apply this formula. We are getting the same graph with redefined weights. And by the way, this redefined weights, they are solutions of some dual linear programming. And then we contract graph. And it's called Blossom because we contracted based on some structures which we discovered both in this LP and this dual LP. And at each step, we start from big graph and we're getting smaller graph. We're getting smaller graph, and number of steps which you need to get basically to resolve it. And at each step you are starting by solving this LP. If you're getting integer solution, you are done. But point is that number of steps which you need to go is not very large, it's not exponential, and we've been able to estimate it. So roughly that, I'm cheating a little bit because unfortunately it's not only contraction, so sometimes you need to expand. But another part, and that's most difficult in terms of proofs, is to show that those expansion cannot happen very often, and actually in overall you are contracting. So therefore, this story is both about graph transformations. This is basically, gauge transformations or belief propagation. So I go from original weights to new weights, and then some contraction. Okay, so let me leave it to that, and yeah, let's have a break and probably for 10 minutes, and then we'll get to finding.